Part 2 of KSP comparing solubilities. You can only compare solubilities by looking at the KSP value if all of the compounds produce the same number of ions. Here you're given 3 salts and their KSP values. Notice that all of them produce one cation and one anion. Silver iodide produces 1 silver and 1 iodine, so that's 2 particles. Copper iodide produces 2 particles, 1 copper, 1 iodide, and calcium sulfate produces 2, 1 calcium, 1 sulfate. So the larger the KSP, the greater the solubility. Looking at it, calcium sulfate has the largest KSP, so it's the most soluble, while silver iodide would be the least soluble. If you don't know the or if they don't all break up in the same number of particles, you have to calculate the molar solubility for each salt. The common ion effect is the same thing that we've seen previously in this chapter, where the solubility of the solid is lowered if the solution already contains ions common to that solid, because it's going to shift left. So here we have 2 solids, silver chromate, and we have a solution of silver nitrate. So you write your dissociation equation for silver chromate, but chromate's a -2, so we need 2 silvers. So it breaks up into 2 silver and 1 chromate. We also have 0.1 molar of silver nitrate, which is a soluble salt, according to the solubility rules, which means it breaks up 100%. So we don't need a KSP value. For that one, we can write our dissociation equation, and just like a strong acid or a strong base, if I have 0.1 molarity, I have 0.1 of each of the products, because it's a 1-to-1 ratio. So I'm starting with 0.1 of the silver and 0 chromate, due to that common ion. Now we're going to solve it the same way. So we have our plus 2x and our plus x. Write the KSP expression, and plug in our KSP value and solve for x. You can ignore the plus 2x just like before because our KSP is so small, it's going to be a very negligible number. So we have 0.1 squared times x is equal to 9 times 10 to the -12th. So x, or the solubility, is 9 times 10 to the -10th moles per liter. Here, you're going to do the same thing. We have calcium fluoride and sodium fluoride. Calcium fluoride is the salt that we're unsure how much will break up. Write your dissociation for the soluble salt. And again, it's a 1-to-1 ratio. So the only one we care about is fluorine, which is 0.0025. and 0 calcium. Notice though, I made a mistake. We need 2 fluorines there, so that's an x and 2x. Plug it into your KSP expression. And you can ignore the 2x like we did a minute ago. Don't forget the square though. Solving for x, you get x is equal to 6.4 times 10 to the -6 molarity. Pause the iPod and try this one on your own. Restart when you think you have the answer. Right, your answer should be B, rounded, and it should actually be 1.36 times 10 to the negative 9th. So silver chloride breaks up into silver and chlorine. 1 silver and 1 chlorine. Sodium chloride breaks up to 1 to 1. So if I have 0.11 sodium, I have 0.11 sodium and 0.11 chlorine. So we have plus X and plus X. Write the KSP expression. Ignore the plus X, and you get X is equal to 1.36 times 10 to the negative 9th. Pause the iPod and try this one. When you think you have the answer, restart it up. So silver chromate, you need to write your dissociation equation. We have 2 silver and 1 chromate. Sodium chromate breaks apart, and we get 0.16 sodium and 0.08 chromate. So we're starting with 0 silver and 0.08 chromate in the beaker to begin with. Plug in the values into KSP. You can ignore the plus X because KSP is so small. You get 4x squared there times 0.08. So solving for x, you get 5.3 times 10 to the negative 6th. And that's molarity, or moles per liter. pH and solubility. If the anion is an effective base because it came from a weak acid, the salt will have an increase in solubility in an acidic solution. So if you look at the 3 examples, they're all weak bases because they came from weak acids. So they would all dissolve better in an acidic solution.